the parallel session 3. In fact, we have instead of 3 talks, we have 2 talks because the third person could not come because of some visa problem. So first speaker is Sameer Murthy. He is going to tell us about functional determinants, index theorems, and exact quantum black hole entropy. Sameer, please.
Thank you. Check. So thank you very much for the invitation. It's a pleasure to speak in front of this audience and also in Bengaluru, where I was born. So that's very nice. So that's my title. In terms of results, my emphasis will be about exact quantum entropy of supersymmetric black holes in theories of n equal to 2 supergravities. And I'll explain that as I go along. Sorry. The computation of exact quantum entropy is made possible using techniques called supersymmetric localization, about which I think most of you know a lot. So this was a program which we began with in joint work with Atish Dabolkar and João Gomes some years ago, and we made quite some progress. And one of the missing ingredients in this program was the computation of a certain functional determinant in theories of supergravity. And I would like to tell you today about progress on this front. Okay? And this computation is possible using index theorems, and that's the 3 aspects of my title. So let me begin with a very brief introduction. So in any theory of quantum gravity, we take the fact that black holes have thermodynamic entropy to mean that they're actually made up of an underlying ensemble of microscopic states. Okay? So in string theory, this expectation is borne out very beautifully and in great detail, starting from the pioneering work of Sen and Strominger and Waffa in the mid-90s. And we have these 2 pictures. Right? So n here roughly generically denotes the quantum numbers of the black hole. So n is the same in both pictures. And there's this parameter called G string. And when G string is, so n can also be thought as the size of the black hole. So when G string is much larger than 1 over n, you have the usual picture of a black hole as a solution of the effective theory with an event horizon and so on. But when G string is much smaller, then you have this picture of microscopic excitations of string theory. And in supersymmetric situations, we expect that, so G string then is a modulus, and we expect that the number of states, or at least the supersymmetric index, does not change when you move in this moduli space. So this statement has caveats because of wall crossing, but this I will not be discussing today at all. So I will assume that there are no discontinuous jumps. And then you can actually compare these 2 pictures. So when we know the microscopic situation very well, that gives us a guide to the macroscopics. And a lot of progress has been made on that front. But of course, the big question is to really understand the gravitational functional integral, to understand the degrees of freedom. And the hope is if we really do that, then we can also try to understand what the microstates are in situations where we don't know what it is yet. Okay, so one very concrete question for gravity is simply how many microstates are there given a black hole? Okay, how many microstates are associated to the black hole? So to be more concrete, that's my aim. So in any theory of 4-dimensional n equal to 2 supergravity, coupled to vector multiplets and hypermultiplets with generic higher derivative couplings. So you can think of this as some string compactification. I would like to compute the perturbatively exact formula for the quantum gravitational entropy of a supersymmetric black hole. Okay, so this is work. So this is based on a paper with Valentin Rijs, who's a student at NICEF in Amsterdam, and also some work with Valentin and Bernard de Witt, which is still in progress. And on the work of many other people, the main inspirations are so the work of Cardoso, de Witt, and Mohab on higher derivative corrections. Augury, Strominger, Waffa, this was the inspiring proposal, and Sen and the quantum entropy function program, and many others. So if something is missing here, please let me know. Okay. Now the story begins. The starting point is really the near horizon of the black hole. So if you have a supersymmetric black hole, then in fact the near horizon region is is by itself a fully supersymmetric solution of the supergravity. And in that sense, and you can decouple it from the rest of the geometry, and in that sense, it's an independent quantum system. You can study it by itself. And the shape of this near horizon geometry is completely fixed by the charges. This is the famous attractor mechanism, essentially because of supersymmetry. So to be concrete, let's consider a 4-dimensional supersymmetric black hole carrying some electric and magnetic charges. The geometry, the metric is ADS2 times S2, and here I've shown you Euclidean ADS2, that's a hyperbolic disk, and an S2, and I've shown L0 and J0, these are symmetry generators of the system. The gauge field strengths are constants, and the scalar fields are also constants. Okay, so all the shapes are completely fixed by supersymmetry. The sizes are not. The sizes are determined by the equation of motion of the theory. And one nice fact is that the classical entropy of the black hole, and by classical I mean given some local effective Lagrangian, including higher derivative corrections, the Bekenstein-Hawking wall entropy, that can be expressed as an extremization problem on this near horizon geometry. Okay? So this is work of Sen, sometimes called the entropy function. And given that fact, it's a natural conjecture to say that the quantum entropy is actually a functional integral over ADS2 field configurations. Okay, so this is the conjecture of Sen, which is the following: is exponential of the quantum entropy, which I shall also call ZADS, is the following. So it's a functional integral. You fix. So imagine the theory to be on ADS2 as a 2-dimensional theory. You fix the boundary conditions of all the fields in accord with the attractor mechanism, which I just talked about, and you let, in the interior, you let all the fields fluctuate, and you're supposed to now compute the functional integral. Now, in 2 dimensions, in ADS2, you can check quite easily that the natural ensemble in gravity is actually the microcanonical ensemble. You just look at the Maxwell field, you'll see that the charge dominates in 2 dimensions over the potential. So everything is a function of charges, and for the same reason, you don't compute the partition function, but the expectation value of a Wilson line with respect to all the electric charges of the black hole. Okay, so that's what this is. So far it's a formal object. The ADS2 means what I just said now. So it has many issues. There are the UV issues of gravity. I'm not going to solve this, so I assume the string theory somehow solves this. And gives you some kind of an effective Lagrangian at finite but non-zero energies. And what I want to do is to use this idea to understand the integration over the light modes. So I write some effective action, and then I want to understand the quantum effects which are non-local coming from the integration over the light modes. There are also infrared divergences because the ADS2 is non-compact, and that needs a certain regularization and renormalization, which has been worked out in this proposal. I'm going to use that. So it's set up in such a way that if you do a saddle point evaluation of the functional integral, then you get back the classical Bekenstein-Hawking wall entropy. Okay? And then you're supposed to compute loop corrections around the classical value. Okay? So the classical entropy, including local higher derivative corrections, has been studied especially in the context of string compactifications by these people. And also the leading logarithmic one-loop corrections has been now computed and systematized by these people. Okay? So that's one way of understanding it. But what I want to do is to really compute this functional integral, not order by order, but exactly. Okay? So I want to compute it at one shot. And the reason I can do that is this method of localization. Okay, so please ask me questions, if there are any. So this is a method which goes back quite a long way. But at least for me, this paper of Pestun really I appreciated the power of this method because of this paper in the context of supersymmetric field theory, and we want to apply this to supergravity. Okay, so you want to compute this functional integral here. So M here is the space of supergravity, the light fields of supergravity, with some measure coming from supergravity. O is this Wilson line, and S is the action of supergravity, including all higher derivative corrections. Okay, it's a formal object because at this level, in principle, this could be infinite derivatives. Okay, but we'll fix this. This geometry admits supercharges, and I'll focus on one supercharge Q, which squares to L0 minus J0, which I'll call H. It's a compact U1 generator. And in this situation, integrals of this form can be solved exactly because of the following. So what you do is you deform the integral by a term qv, which I've written here. Lambda is a positive non-negative number, and what you really want is I of 0, but you can show that this integral is independent of lambda, and therefore I of 0 is equal to I of infinity. But when lambda is very large, then this term dominates, right? In fact, as lambda goes to infinity, you get a semi-classical approximation. So that's really the idea of localization. Semi-classical means you should look at critical points of QV, but if you stare at this, it actually means you just look at solutions of cube psi equal to 0, where psi runs over all the fermions of the theory. Okay? So you need, in order for this to work, you need an off-shell supersymmetry algebra because these manipulations are going on inside the functional integral. So you do that. Therefore, the full infinite dimensional functional integral reduces to this finite dimensional object, which are the space of solutions of off-shell BPS equations. And then there's some induced measure, the same O, the same e to the minus s. You can check that at the critical points, actually QV has 0 value. So you just get e to the minus s. And then semi-classical means that you also have to have a one-loop determinant, and that's what I've written here, of this QV action, the deformation action. Okay? Sorry? This? M. So this d mu is the measure of supergravity, of the field space of supergravity, and d mu q is the induced measure on this submanifold. Okay. So we want to now do this for supergravity, and this was done in a sequence of papers with Atish Davolkar and João Gomes. And here are the basic steps. Roughly each of them was one paper. So first, well, not this one. First, we need a formalism where the off-shell supersymmetry is realized in supergravity. Then we want to find all solutions of the equation cube psi equal to 0, subject to the boundary conditions that I discussed. Then I want to find the full supergravity action evaluated on this solution. And finally, I want to compute the quantum measure, which includes this d mu, but also the one-loop determinant. Okay, so these are the 4 steps, and I'll very briefly go through each of these steps now. What time is it? 18 minutes, good. Sorry? 13. Okay. So what's the formalism? So the formalism goes back to the 80s. It's called conformal n equal to 2 supergravity. Essentially, you have supergravity coupled to NV physical multiplets, and in the formalism, you need actually to put one more vector multiplet. Sorry, I meant vector multiplets. And so you enlarge the field space, and therefore you gain more symmetry. You get some conformal symmetry. This makes an off-shell supersymmetry easy to write down. And here is how the conformal symmetry acts. Each of the scalar fields of the vector multiplets scale like so, and the metric scales like so. And then you have one extra field, and you have to put some gauge conditions. Okay, so one field which is important is the following. It's called e to the minus k. Sometimes k is called the generalized scalar potential, which is written in terms of the scalar field and Fi. So F is the holomorphic prepotential of n equal to 2 supergravity, and Fi is the derivative of F with respect to xi. Okay. So this field appears in the action as such. It's square root of minus g e to the minus k times r. So you can see that it plays the role of the conformal compensator or the dilaton field. And now we want to gauge fix. So often one uses the gauge e to the minus k equal to 1 to get back Einstein-Hilbert, but one can equivalently put, there should be a minus sign here, square root of minus g equal to 1. And that's the gauge that I shall pick. And in this gauge, so the reason that's a nice gauge to pick is because the symplectic symmetry now acts linearly. There's no constraint on the field space, and there's a linear action. And in this gauge, you can see from this term that e to the minus k actually measures the size of ADS2. Okay? Okay, so that's the formalism. Then you want to look for all BPS solutions. So this was a longish story. I'll just tell you the bottom line. So in the gravity multiplet, in this gauge, there is no other solution. You only have the full BPS solution. This was work with Rajesh Gupta. And in the vector multiplet sector, there are non-trivial solutions. And the solutions involve the scalar field going off shell. So this is ADS2. You can write down a formula, but I thought this is more instructive. So towards infinity, the scalar fields go towards their attractor values. It need not be 0. And then it has a shape. Again, the shape is fixed by supersymmetry, by the off-shell BPS equation. So it kind of rises, goes to a maximum or minimum at the center of ADS, and then falls back again. So this is a radial profile, and it's symmetric in the azimuthal angle. And this value phi I is a modulus. That's not fixed by supersymmetry, and you have to integrate over that from minus infinity to infinity. Okay? So the bottom line is that this localization manifold onto which the integral collapses to is labeled by one parameter for each vector multiplet xi. The classical measure for the scalar manifold has been computed by Bernard and Swapna and Cardoso, and this does not scale with respect to the charges when I make the charges very large. Okay, so that's the formalism. That was the off-shell solutions, and now the action. So the generic action of n equal to 2 splits into two types, so roughly f terms and d terms, more precisely chiral superspace integrals of holomorphic functions and full superspace integrals. Now the chiral superspace action is much more under control as usual, and this is governed by one holomorphic function called the prepotential f, and this actually is computable in string theory. For instance, if you have a Calabi-Yau compactification, this f is computed by the topological string. And this, the action governed by f on the localization manifold takes a very simple form. I'll show you in a second. But now you have the d terms, but luckily we don't have to worry about them. Okay, so you can show, this statement has some caveats, not a complete theorem. You can show that essentially only the chiral superspace integral matters. Okay, so therefore you're actually reduced to something controllable. And now you want to put this in the action, and when you do that, what you get is something like so. Okay? So what you get is the functional integral reduces to this NV plus 1 dimensional manifold with some classical measure m times the classical action reduced to something very simple. So the exponential of the action, which is simply the Legendre transform of the imaginary part of the prepotential evaluated on phi I plus IPI. Okay, so this begins to look a lot like the OSV formula. And there's also this one loop determinant in the localization formula of the QV action as a function of the phi I. Yes? Speak up, please, yes? Yes, yeah. So, yeah, so good. So far I've just, so this is for gravity plus vectors. We can do the same thing for hypers, and I'll tell you in a second. For one supercharge, you can actually write that down. So indeed, that's the problem for, you can't write it, a Lorentz invariant formulation is not known with a finite number of auxiliary fields, but for one supercharge, you can do that. Okay, so I won't show you the details where you can talk about this, you can certainly do that. Okay, so today what I want to tell you, so this was the formula which we reached with Atish and João, and today what I want to tell you is progress on this front. Okay? Other questions? Okay. Now, firstly, why is there a one loop determinant at all? You have a theory of abelian vector multiplets on something. Why do you get anything non-trivial? And the reason is that there's a scale in the problem, and the functional determinant can actually depend on the scale. And in fact, that's the only thing it depends on, and that's what we want to capture. And remember that the length scale in the off-shell formulation is given by this field e to the minus k. And at the center where the localization coordinates are, center of ADS2, this L square is given by e to the minus k as a function of the localization coordinates phi I. Okay, so it depends on where you are. And the main result is the following. Okay, so we found, so this is this work with Valentin Reis, that the one loop determinant as a function of phi I is just exponential of minus a0 times k, this field k, where a0 is a number which is a linear combination over multiplets. For each multiplet, you can compute a0, and so that was the first part of the result. And the second part is that you can compute a0 using index theorems. And the answer, so what we did so far is vector and hyper multiplets. So this is where we need the formalism. And you have vector multiplets, a0 is minus 1/12, and hyper is plus 1/12. Okay, so that's the main result.
You add a localizing plot for the hypers also?
Yes.
So
Yeah, again, so here we made an assumption. We haven't solved for all solutions of the hypers, and I'm assuming that the classical solution where there's only constant is the only one. But otherwise, yeah, there's this psi, cube psi, where psi runs over all fermions. So it's a sum over all the fermions of the theory, including the hypermultiply fermions. Okay, so we're currently we're doing in discussion with Valentin and Bernard de Witt, also the graviton multiplet. That's still in progress. Okay, how much time do I have? 5 minutes. Okay, so then maybe I was going to give you a very brief sketch. Well, very, very brief. So you separate, the computation goes as follows. You first, everything is algebraic, only depends on supersymmetry. You separate the fields into doublets under Q, and then you call X and psi the fundamental bosons and fermions. You find some operator D which relates the two, and the determinant is related to the determinant of H. And the determinant of H is encoded in the index of this operator D10. Okay, the supersymmetric index. And this index, and the reason this is nice is because this index is computed by a very powerful fixed point theorem due to Atiyah and Bott, which tells you that the index actually reduces to the fixed point of the space-time action of H. Okay, so that's very simple. You just have 2 points here, the center of ADS and the poles of the sphere. And therefore, the problem reduces to a quantum mechanics problem. Okay, so all you have to find is write down all the fields in your theory and compute what their charges are under these rotation generators at the fixed point. Okay, and just plug that into the index formula here, and this determinant is very easy to compute. That is essentially a Jacobian factor. Okay, so I skip lots of details, but that's just to tell you that once you've written everything in the off-shell formulation, the calculation becomes completely automatic because of the index theorem, and you just get some answer for the index like so, and then you can just read off what the eigenvalues of H are and what the degeneracies are, put them back into the determinant, you get some infinite product. This needs to be regularized, and we use some zeta function regularization. Okay, so just a very brief sketch of how to do that. And that's, so again, okay, very quickly, again, some technical comments. In supergravity, actually, if you look at the square of the supersymmetry, it doesn't square to L0 minus J0, it only does so up to some gauge transformation. So you have to fix that by introducing some ghost fields and BRST operators. You have to build a new operator called Q hat, which depends on both Q and QB, and Q hat square actually squares to L0 minus J0. And in terms of this Q hat, everything is algebraic. Everything is paired up. There's a cohomology, and you can literally just run the machine. There's also certainly about boundary modes. These are pure gauge modes with gauge transformations that are non-normalizable, but the mode itself is normalizable. Those need to be treated separately. That's been done here, and this measure for these modes needs to be dealt with separately using arguments of ultra-locality, first due to Witten. Okay, so those were was a very brief description. Some checks. So this is the main formula. When you take all charges to be very large, you can show that our formula reduced to something like this, where the coefficient, so this is Bekenstein-Hawking, is the log correction, and this A0 is literally the A0 that I told you about. And this A0 has been computed by on-shell methods by many people, as I showed you earlier, Sen and collaborators, and also Finn and collaborators, and it agrees. Another check you can do is microscopics of n equal to 8 string theory. So in a series of papers with Dabulka and Gumsh, we actually truncated the n equal to 8 supergravity to an n equal to 2 theory. So we threw away a lot of fields, and in that theory, we ran the localization machine using an assumption about the measure, and that gave us, on the nose, integer microscopic degeneracies, after including non-perturbative corrections as well, starting from gravity. And now you can check that indeed the things that we throw away, we're justified to throw away, because the only way they'll contribute is through the one-loop determinant, but they add up to 0. Okay, so that's another check. And this is my last slide. So here's, so my aim was to find some exact formula for half BPS black holes. As I said, this was inspired a lot by the OSV proposal. And here's what it looks like. So this is where we're going towards. There are things to do yet. This formula looks, is really the formula by Denef and Moore, who kind of refined the OSV proposal. and was written down by looking at microscopic conformal field theories in n equal to 2 supergravity, the duals of n equal to 2 supergravities. Okay? We still have to complete this graviton calculation, and there's this classical measure factor which I didn't tell you about. At two derivative level, the classical, if you borrow the classical measure factor which Bernon and Swapna and Cardoso write down, then you get really exactly this formula. Okay? So that's quite surprising, because when Denef and Moore wrote down this formula, it was based on, in a regime of large topological string coupling. And here we have a derivation at weak topological string coupling. Okay, so there are caveats, but that's where we are headed. And the fact that you begin to get a formula which looks similar actually implies a surprising cancellation of states in an equal to string theory. So this was not known so far. Am I completely out of time? Okay, well, maybe just one thing. There was an old puzzle about the topological string. This is the usual, this is the way we write the topological string partition function. And there were comments that if you analytically continue to weak coupling, so this is at large coupling, lambda, you get this extra log term. Okay? And one puzzle was how to interpret this from gravity. And now we really understand this as just what it should be. It just arises not as the Wilsonian effective action, but as so the puzzle was that it doesn't arise at any order in perturbation theory. How does that happen? Now you see that it arises as the 1pi effective action. Okay, so let me stop. I'll stop with this slide here. Thank you.
When you do the n equal to 8 calculation, you also have the extra gravity in
Yeah, so I should have mentioned something. So what we're doing right now is both graviton and spin 3/2 multiplets. And this we haven't done, but what we can do, so we know the form always has to be of this form e to the minus k times some a naught. And then consistency with the large charge approximation implies that a naught has to be 2 and minus 11 or 12, something like this. And if you plug that in, you can check that there's a cancellation.
I see. But when you said that you showed that the things which you had ignored are actually
They
zero.
were cancelled, so I assumed this. I assumed what I just said.
I see, okay.
Yeah.
Okay.
Thank you. Yeah, I should have mentioned.
I had the same question.
Huh? So I can hear you.
This is just a comment, perhaps. Yes. I think to use functional methods in trying to compute black hole entropy, I think the good test ground would be 5D black holes. It's much simpler, but still hard, very hard. To try to apply to get exact formulas for 5D spinning black holes using the same formulas.
Okay, thanks.
Any other question?
So is phi here real?
So it needs a contour prescription. So in n equal to, so it's 1 degree, 1 real degree of freedom, but you need a, so in n equal to 8 theories, we know exactly what the microscopic theory is, and it really comes out of a formula like this. So what you can check is that, so there it reduced to an 8-dimensional integral. 7 of them are Gaussian, and one of them you need a contour of the Bessel function. So you need a contour prescription in the.
And in e to the minus k, the phi there, is it the same phi?
It's the same phi.
And this k is the Kähler potential?
So it's what is called the generalized scalar potential. It has nv plus 1 degrees vector multiplets.
But in the Kähler potential, the argument is always neither holomorphic nor anti-holomorphic, so it has both. And you say that phi is real.
Yeah, so it's just a function k, and it's evaluated at real k. That's what this thing tells you.
And what happens if you do, say, Kähler transformations on this k, which would not affect the answer?
So Kähler, no, so I chose a certain gauge where I fixed the metric, and in fact now the nv plus 1 vector multiplets are all independent. Okay? And then there's some function e to the minus k which comes out of that, and what this is, so it indeed comes from the Kähler potential of the supergravity, but the imaginary part, you mean? Yeah.
It's fixed by the magnetic attractor equations. No, not anymore because no.
It's K of phi actually, I think. Yeah. That's right, that's right. So here, this is just, yeah. It's literally it's the length scale of the ADS2. You're asking if this has an imaginary, if this has a phase.
How would it expect the phase to be real?
Mm-hmm.
Be a function of complex and great complex quantity.
IP. No, here I think it's just really phi. Yes. And phi minus, yeah, that's right, that's right. That's what I'm doing, yeah, exactly. Yeah, thank you, yeah, exactly. Thanks, okay. It's there implicitly, yes, thank you. Yes.
Okay, I have one more question
Yes.
about the hypermultiplets.
Yes.
So typically the hypermultiplets are not fixed by the attractor equation, right? It's completely
Yeah,
arbitrary.
yeah.
But the localizing term that you are adding,
Yeah.
that fixes the hypermultiplet somehow?
No, so that's one thing which we haven't figured out yet. So the hypermultiplets, we assume so that there's a constant value, and we don't integrate over, so we don't understand that yet. So there's a constant value.
Yeah.
The term we are adding is just, will again tell you that it's a constant value without fixing the value of the constant. So maybe there's
So it's some derivative of phi squared?
That's
I mean,
right,
is that
something like that, yeah,
I see.
exactly. Right. It's essentially a free field, so with q lambda, so that essentially looks like a kinetic term. That's right.
I see.
So that's one thing I still don't know how to do for hypers,
Yeah, last question. Yeah.
Sorry, you said that the only solution, you said earlier in your talk that the only solution that contributes is ADS2 cross S2.
Yes.
Is there something special about ADS2? Do you expect it in some other cases as well? Or if that's the case, then why do you want to still do a graviton calculation?
No,
the Weil multiplet
so
calculation?
to answer your second question first, the graviton calculation is still in here because remember, if I chose a different gauge where e to the minus k is 1, the determinant of the graviton still fluctuates. Okay, so that's certainly part of the NV plus 1 integrals. To answer your first question, yes, it depends on ADS2 quite crucially. So in general, you don't expect that solving one supercharge equation just fixes everything to be only full BPS. In this case, you get that one supercharge, you assume some complex nature, you get 2. There's a surprise that in fact you get 4 supercharges to be fixed. And then imposing Euclidean ADS2 times S2 boundary conditions fix that. And that's quite important. So I don't expect this in higher dimensions.
Okay, so let's thank Sameer for the nice talk. So the next speaker is Masaki Shigomori. He's going to tell us about Habermas superstratum.